Hey everyone, welcome to Math 104, section 7.7 on complex numbers. Please start with a warm-up. So we're going to simplify these radicals. We have a square root, so we want to break this up into a perfect square. So that'll equal square root of 16 times the square root of 2. Square root of 16 is 4, so we get 4 square roots of 2. And then with 75, a perfect square that's a factor of 75 is 25. So that's the square root of 25 times the square root of 3. So 5 square roots of 3. So the first thing we're going to talk about today is imaginary numbers. And it's kind of an unfortunate name for the number. They gave it that name because they weren't sure if it was something real. It's definitely not a real number in the sense of the real number system where we've got all the integers and decimals and all the irrational numbers like the square root of 2 or pi. But they weren't even sure if it had any real application. It wasn't for another couple hundred years that physicists started using this to describe things like electromagnetic waves and electronics. So the imaginary numbers do have real applications, and they do mean something in the real world. Now, a complex number is made up of two parts. Think of this as being like the binomials that we've studied so far in this course. We have the real part over here, which is just any real number. And then over here we have the imaginary part, which is some real number b times I, the imaginary number I. So I is defined to be the square root of -1. Now that's something we've never been able to do before. Whenever we've had roots that have a negative number as the radicand, well, we just haven't evaluated those because they aren't real numbers. Well, this is going to allow us to do those, which is going to open up a whole new class of problems for us to solve. So in simplifying complex numbers, we need a property to use. So this is, by definition, going to be I times the square root of a. So this is the property then we'll be using to simplify complex numbers. So let's take a look at an example of this in practice. All right, we're going to simplify the square root of -16. So we're going to use this property here and write that as I times the square root of 16. Square root of 16 is 4, so that gives us 4i. Part B, with some of these, we're going to just leave the radical right in there if it doesn't evaluate to an integer. So the square root of -3, using our property here, we get I times the square root of 3. Cannot be simplified any further, so we're going to leave it just like that. Now traditionally we write the I before the radical because it can be kind of difficult to see whether or not the I belongs underneath the radical or if it belongs outside the radical if you write it afterwards. So to avoid that confusion, we just write the I in front. Next up, negative square root of -9. Right, so we use this property again, just don't lose the negative out front because those two negatives don't cancel. All right, so using this property, that gives us negative times I times the square root of 9. And the square root of 9 is 3, so this turns into -3i. And then D, square root of -18. And we'll need to do a little bit of simplifying here. So that gives us I times the square root of 18. Now let's break up 18 into a perfect square factor. So we got I times the square root of 3, or the square root of 9, jumping ahead there, times the square root of 2. And the square root of 9 is 3, so that turns into 3i square roots of 2. Your turn, number 1. First one, square root of -7. Just use the property and we're done. Cannot be simplified. Here, we get I times the square root of 24. Now this can be broken up into 4 times 6. So this can be I times the square root of 4 times the square root of 6, which equals 2I square root of 6. All right, this one, we got I times the square root of 4, which is 2I. And for this one, we got the negative I square root of 64. Square root of 64 is 8, so that's negative 8I. Now something we have to be careful about. You see something like this. We've got the square root of -4 times the square root of -9. Now we have that product property, which allows us to multiply the two numbers underneath the radicals together, something like this. Square root of -4 times -9. But we cannot do that because the product property only applies to positive numbers. 0. But it does not apply to negative numbers. So the product property cannot be used there. And notice if we did that, we'd get the square root of positive 36, which is 6. So we get positive 6 if we do it that way. That's not correct, so don't do it that way. We're going to do it like this, using what we just saw, which is rewrite square root of -4 as I times the square root of 4. And then rewrite the square root of 9 as I times the square root of 9. All right, and that becomes 2I times 3I, which is 6I squared. And we just saw the definition of I squared is -1. That equals -1 by definition. So we get -6. We should get -6 with that instead of positive 6. All right, next example, we got the square root of -16 times the square root of -49. All right, so that is I times the square root of 16 times I times the square root of 49. And that gives us 4I times 7I, which equals 28I squared, which is 28 times -1, which is -28. Your turn, number 2. Square root of -4, that is I times the square root of 4. Square root of -25 is I times the square root of 25. So that equals 2I times 5I, which is 10I squared, which is 10 times -1, which equals -10. Next example, square root of -6 times the square root of -10. That's I times the square root of 6 times I times the square root of 10. Right now, in order to simplify these, now we can use the product rule. So write this as I squared times the square root of 60. Now we can simplify square root of 60. So 60 can be broken up into 4 times 15. So that gives us I squared is -1 times the square root of 4 times the square root of 15. This is 2, so that gives us -2 square roots of 15. Your turn, number 3. We write this as I times the square root of 12 times I times the square root of 21. And we could use the product property and multiply those two together. But it might be easier to go ahead and break them up, because we do have a perfect square here, factor. So let's do that. Now I've got I times I, which is I squared. And we'll break this up into the square root of 4 times the square root of 3. And this we can break up into the square root of 3 times the square root of 7. All right, I squared, that's negative 1. Square root of 4 is 2. Square root of 3 times the square root of 3 is 3. And the square root of 7 remains. Multiply all this out, we get negative 6 times the square root of 7. All right, next up, we're going to simplify. Square root of negative 40 over square root of negative 10. So we'll start off using our property. I times the square root of 40 over I times the square root of 10. Now i's will cancel just like a variable, so those go away. And then here, we can use the quotient rule. So that gives us square root of 40 divided by 10, which is the square root of 4, which is 2. Your turn, number 4. All right, so it gives us the I times the square root of 80 over I times the square root of 5, using our property. Now the i's cancel, and we can use the quotient rule. So it gives us the square root of 80 divided by 5, which is the square root of 16, and that's 4. We won't always have a cancellation. Got negative square root of negative 75 over the square root of 3. All right, so we got that I up top. Nothing to cancel with, so we're going to keep that. Now we can use the quotient rule here. So that is I times the square root of 75 over 3. And as I times the square root of 25, that's 5, so we get 5i. Your turn, number 5. Square root of negative 64 over the square root of 16. Oh, this one, we don't even need to use the quotient rule because we have a perfect square here and a perfect square here. So that is 8i over 4 or 2i. Now, adding or subtracting complex numbers ends up being just like adding or subtracting binomials. When doing addition or subtraction, you could just consider I to be a variable, just like x. It is exactly the same way. There will be some important differences once we start multiplying, but with adding and subtracting, it's just combining like terms. Alright, so we're going to add a couple of complex numbers together. We'll add the real parts together. 2 plus 3 is 5. And then we'll add the imaginary parts together. 4 plus -1 is 3. So we get 5 plus 3i. Your turn, number 6. We have 3 minus 5i plus 4 plus 9i. Adding together the real parts, that is 7. Imaginary parts, -5 plus 9 is 4, so plus 4i. 7 plus 4i. Now we can do subtraction. Seven plus 4i minus 2 minus 3i. Nothing tricky here, just make sure you're subtracting both of these terms. So we got 7 minus 2, that's 5. And look out for subtracting a negative. 4i minus -3i is the same as 4i plus 3i. So we get 5 plus 7i. Your turn, number 7. We get 8 minus 2 gives us 6. And -3 minus -7 is -3 plus 7, so that is plus 4i. 6 plus 4i. Alright, now we're going to multiply complex numbers. And the only difference between multiplying monomials and multiplying, or monomials and binomials, and multiplying complex numbers is when we encounter I squared. So first example, we've got 3i times 5i. Right, multiply number by number. 3 times 5 is 15. I times I is I squared. So if I were a variable, we'd stop right there. But it's not. I squared is -1, so we got 15 times -1, which equals -15. Your turn, number 8. Four I times 7i. 4 times 7 is 28. I times I is I squared. We'll convert I squared to -1. So we get -28. Alright, so now we can combine these properties with standard algebra techniques like distribution and foiling. We're going to multiply 3i by 8 minus 2i. Distributing in, 3i times 8, that's 24i. Now we got 3 times 2 is 6, so we're going to subtract 6, and then we have I times I is I squared. Alright, so that gives us 24i minus 6 times -1. Now here's where it gets a little tricky. Alright, bring down the subtraction. Now we're going to do this multiplication. What do we get here? 6 times -1 is -6. I see a lot of students lose a negative sign in there, so you end up with 24i minus 6. Well, we shouldn't have that. We should have 24i plus 6. And then writing in standard form, it's traditional to write the real number first. So that gives us 6 plus 24i. Your turn, number 9. We're going to distribute 5i into 6 plus 4i. 5 times 6 is 30, so we get 30i there. Plus 5 times 4 is 20. I times I is I squared. I squared to negative 1. So that gives us 30i minus 20. We'll flip those around, negative 20 plus 30i. All right, next up we're going to FOIL. 4 minus 6i times 2 plus 5i. All right, FOIL. First times first. 4 times 2 is 8. Outside, 4 times 5i is 20i. Inside, negative 12i. And last, negative 6 times 5 is negative 30. I times I is I squared. Now we can combine like terms. 20 minus 12 is 8, so that gives us 8i here. And here, we're going to get minus 30 times negative 1 for I squared. All right, this becomes 8 plus 8i minus negative 30, which is 8 plus 8i plus 30. So that gives us 38 plus 8i. Your turn, number 10. FOILing. 3 times 5 is 15. 3 times 7 is 21, so we get 21i. And here we got negative 8 times 5 is negative 40, so negative 40i. And negative 8 times 7 is negative 56. I times I is I squared. Combining like terms, 15 minus 19i. And then over here we got a negative, or minus 56 times negative 1. So that gives us 15 minus 19i minus negative 56. So we're going to turn this into addition. So that's 15 minus 19i plus 56. And we can combine constants. It's 71 minus 19i. Now dividing complex numbers is going to require the use of what's known as the complex conjugate. And we've seen a conjugate before when we worked with radicals, and it's the same idea, but with imaginary numbers. So just like we couldn't have any radicals in the denominator to simplify, we can't have any imaginary numbers in the denominator if we want to simplify. And it's just another example of this process called rationalization. It means we want to create a rational number, and that requires a real number in the denominator, other than 0, of course. So complex conjugate, we got the same terms with the opposite sign. So a complex conjugate of a plus bi is a minus bi. And if we start with a minus bi, complex conjugate is a plus bi. So we're going to simplify (4 minus 3i over 2i). So goal in simplifying is to get rid of any imaginary numbers or complex numbers in the denominator. So how do we get rid of an I? We're going to turn it into negative 1 by multiplying both the numerator and denominator by I. All right, now we have to distribute the I in the numerator. So that gives us 4i minus 3 times I squared. And in the denominator, we have 2 times I, so 2i squared. Now converting those I squareds into negative 1 gives gives us 4i minus 3 times negative 1 over 2 times negative 1. So that gives us 4i minus negative 3 up top and negative 2 on the bottom. So we get negative 4i plus 3 over 2. Now if we want to write this in a standard form, we need to break up this fraction. Alright, so we've got that property, or if we have things added or subtracted up top over a single number on the bottom, we can break that up into two fractions. So that'd be negative 4i over 2 minus 3 over 2. Now we can simplify this part into 2i, negative 2i, minus 3 halves. Now here's the real part, so we're going to write that first if we want to put it in standard form. So that's negative 3 halves minus 2i. Your turn, number 11. This is just like last time, we're going to multiply by I over I, so we can get rid of that I. Distributing in, we get 7i minus 6 times I squared over 3i squared. Let's convert the I squareds into negative 1. Alright, that gives us 7i minus 6 times, or minus negative 6 over negative 3. So we get 7i plus 6 over negative 3. So I'm going to switch these around. Since we're adding here, we can just flip them. So that'll be negative 6/3 minus 7i over 3. This becomes negative 2. So that gives us negative 2 minus 7i over 3. Now, if the denominator is a complex number, then we're going to have to multiply by the complex conjugate over itself. Now, when we did this with radicals, we noticed that when we did that, all the radicals would disappear. We're going to get the same thing by multiplying by the complex conjugate. Alright, so we look at the denominator. We have 3 minus 5i. The complex conjugate of that is 3 plus 5i. So we're going to multiply by 3 plus 5i over 3 plus 5i. Now we're going to need to FOIL on top. So 7 times 3 is 21. 7 times 5i is 35i. 2i times 3 is 6i. And 2i times 5i is 10i squared. Now on the bottom, just like we saw the radicals, we've got the factored form of difference of squares. So all we need here is the first term. 3 times 3 is 9, minus square root of the second term. 25i squared. So a little time saver there if you remember your difference of squares formula. Alright, up top we're going to do some simplifying there. So that gives us 21 plus 41i plus 10 times negative 1 over 9 minus 25 times negative 1. So that turns into 21 plus 41i minus 10 over 9 plus 25. I'm going to skip a step there. 9 minus negative 25 is 9 plus 25. So that gives us 21 minus 10 up top So we got 11 plus 41i on top. Then 9 plus 25 is 34. So bringing that up in a standard form, we got 11 34ths for the real part. And 41 34ths I for the imaginary part. And that brings us to your turn, number 12. So we got 5 plus 8i in the denominator. So we're going to multiply by the complex conjugate of the denominator over itself. 5 minus 8i over 5 minus 8i. All right, we're going to FOIL on top. 2 times 5 is 10. Outside, 2 times negative 8i is negative 16i. Inside, negative 15i. Last plus 24i squared. Now the denominator, got our factored form of difference squares. So we do first times first, 25, minus last times last, 64i squared. All right, now let's convert the I squared to negative 1 and combine like terms. So 10 minus 31i plus 24 times negative 1 over 25 minus 64 times negative 1. So that gives us 10 minus 31i minus 24 over 25 plus 64. And 10 minus 24 is negative 14 minus 31i over 89. Now we can split this up into negative 14 over 89 minus 31 over 89i. Next example. Negative 7 plus 4i over 3 plus 2i. We're going to simplify this, so we'll multiply by the complex conjugate of the denominator. Now if you forget and actually accidentally use the complex conjugate of the numerator, you'll see that it's not going to simplify. So should be a pretty big clue that you started that one off wrong. Okay, negative 7 times 3, negative 21. Negative 7 times negative 2i, that's positive 14i. Here we got plus 12i in the middle, the insides, and then we got negative 2 times negative 4 is negative 8, and I times I is I squared. All right, bottom, 3 times 3 is 9, minus 2i times 2i is 4i squared. So we got negative 21. We're going to combine like terms here. That is 26i minus 8 times negative 1 over 9 minus 4 times negative 1. All right, subtracting negative 8 is adding 8. And over here, subtracting a negative 4 is adding 4. So 9 plus 4 there. Now we can combine the constants on top. Negative 21 plus 8. That gives us negative 13 plus 26i over 13. Now at this point, we need to do some factoring. Notice we have a common factor of 13 up top. So we can factor out 13. That gives us negative 1 plus 2i over 13. All right, now we've got a common number on top and bottom. We'll cancel the 13s and we get negative 1 plus 2i. So when you get to the end, make sure you look for opportunities to factor and cancel. Your turn, number 13. We're going to multiply by the complex conjugate of the denominator, which is 7 minus 3i over itself. All right, foiling on top. Negative 38 times 7, can't do that one in my head. Negative 266. All right, outside, negative 38 times negative 3. It's going to be positive 112i. Inside, negative 8 times 7, that's negative 56i. Negative 114, yeah. Close. And negative 56, okay. Last, negative 8 times negative 3 is positive 24i. All right, on the bottom, we got 7 times 7, that is 49, minus 3i times 3i, or 9i squared. Right, now we can combine like terms in the middle here. So we got negative 266 plus 58. Yep, 58i. Oh, that's supposed to be I squared there. So now we've got plus 24 times negative 1 over there. And here we got 49 minus 9 times negative 1. So that's negative 266 plus 58i minus 24 over 49 plus 9. Now we can combine negative 266 and negative 24. So that's negative 290 plus 58i over 49 plus 9 is 58. So this is a pretty big clue that we're going to be able to factor 58 out of this thing. Well, as it turns out, 290 is 58 times 5. So let's factor out a 58 and get negative 5 plus I over 58. The 58's cancel, and that gives us negative 5 plus I. All right, next up, we're going to work at simplifying powers of I. So I'd like everybody to do is perform a little experiment. Let's look at the powers of I and see if you see a pattern developing as we go from I to the first, to I to the second, I to the third, I to the fourth, and so on. What's the pattern there? So as we go up in powers of I to the first is I to the second is -1, I to the third is -I to the fourth is 1. I to the fifth is -I to the sixth is -1, I to the seventh is -I to the eighth is 1, I to the ninth is I, and yada yada yada. So we're repeating every 4, and we can use that to simplify powers of I. Alright, so what we're going to do is use our properties of exponents. Alright, I to the 20th. Now this one's a multiple of 4, so we can rewrite this as I to the 5th, I to the 4th to the 5th power. Remember, with power to a power, we multiply the exponents. So just take 20 and divide by 4, and that'll give you the outer exponent. So I to the 4th to the 5th. Now, what was I to the 4th? That's 1. So now we have 1 to the 5th. And any number, or 1 to any power, is just 1. All right, so that's how you can simplify any exponent of I that's a multiple of 4. But what about the exponents that aren't a multiple of 4? Let's try b, I to the 13th power. Okay, now here's where we're going to break it up. We're going to break it up into I to the 12th times I, because 12 is a multiple of 4. And as we've seen, anytime we have I to a multiple of 4, we get 1. So this is 1 times I, or I. C, I to the 26th power. Now let's do that again. We're going to break it up into I to the 24th times I squared. I to the 24th, that's a multiple of 4, so that's 1. So we got 1 times I squared. I squared is -1. So that gives us 1 times -1, which is just -1. And then part D, I to the 31. We'll break that up into I times 28, or I to the 28th times I to the 3rd. 28 is a multiple of 4, so that's 1. So 1 times I to the 3rd power. And I to the 3rd power, we found, was -I. So this is -I. And now let's try a -1. So we're here, e, I to the -19th power. Right. So we're going to use the definition of negative exponent. That'll be 1 over I to the 19th, which is 1 over I to the 16th times I to the 3rd. And here's our multiple of 4, so that's 1. So that gives us 1 over I to the 3rd, which equals 1 over -I. But you can't leave I in the denominator, so we need to rationalize. So now we'll multiply by -I over -I. I mean, positive I over positive I. That gives us positive I in the numerator. We have -I times I, or -I squared in the denominator. All right, now we got I in the numerator. I squared turns into -1, so we have negative of -1. Well, that's just 1, so we get I. Your turn, number 14. First one, I to the 22nd power. We can break that up into I to the 20th times I squared. 20 is the power of 4, so this turns into 1. So that gives us 1 times I squared. I squared is negative 1. 1 times negative 1 is negative 1. Part B. 32 is a multiple of 4. So that will be I to the 4th power to the 8th power, which is 1 to the 8th, which is 1. Got another negative exponent there, so we'll write that as 1 over I to the 9th power, which is 1 over I to the 8th times I. I to the 8th is 1, so this is 1 over I. Right now we will rationalize, so multiply by I over I, which is I over I squared. I squared is negative 1, so that's I over negative 1, or negative I. I to the 17th. Break that up into I to the 16th times I. I to the 16th is 1, so 1 times I is I. And I to the 27th. We'll break that up into I to the 24th times I to the 3rd. 24 is a multiple of 4, so that is 1. So we get 1 times I to the 3rd. And as we saw earlier, I to the 3rd is negative I. It's important to have very strong fundamentals using imaginary and complex numbers. We'll be using these to solve problems in the next section, and these will be used extensively in college algebra.